Hi, it's Dubler with Imply. You don't want the users of your analytics application to be sitting around waiting for things to happen. You need to deliver interactivity at any scale. Whether you measure that scale in data volume, such as terabytes and petabytes, or in queries per second, or even in the number of concurrent users, you need a database that can deliver sub-second in any of those situations. So let's see how Druid does it. To deliver interactivity at any scale, you need a database that has three characteristics. The first is coordinated processing, hybrid architecture, and also an efficient storage engine. So let's talk about what each of these means and how Druid deploys them. Now, for coordinated processing, what we mean by that is simply that you have several different independently scalable node types for your cluster. For example, with Druid, you have three major node types. You have master nodes, which control the overall health of the server. You have query nodes, which obviously process queries. And then you have data nodes. Now in this case, I'll draw two data nodes, but you can have one of these. In fact, you could have one physical box doing all of these roles, or you can scale this out to thousands of individual servers if you need to. I'll draw two data servers there. And then underneath all of this, we have a deep storage layer, which can be run in the cloud, for example, on S3, or if you're going to do this old school and do it on premise, it would be Hadoop. Now, most of our competition only has one node type, which is the query node. The reason that you need to have many of them and that you need several different types and that you need to be able to scale them independently is because we know that coordinated processing is the key to scaling out, which is the way you need to go if you're trying to accommodate more users or more queries per second. Not scaling up, but scaling out. And so when you need to scale out with Druid, for example, if you want to add a query node, you can simply add one, but then you can also add more data nodes if you need to as well. And because of this hybrid architecture where we have both local components and separate storage, so this is basically separate storage and compute, we can use deep storage to basically redistribute the workload, rebalance the workload across these data nodes automatically, something that our major competitor cannot do. They require downtime and manual effort. But in order to scale out to meet the needs that you'll have in the future, it helps to have this hybrid architecture. It gives you the flexibility. But because we also have an efficient storage engine at this data node layer, you also get all the benefits that you would have under a more traditional, say, shared nothing approach. When data comes into the cluster, we store it in segments, and I'll draw three of them here under that one data node. When data comes into segments, what happens is we columnarize them, we compress them, we partition them, and we index them. So every one of these is going to have an index on it. And then you typically would partition data by time on these, and so you'd have pretty much all of the records from the same time on each of these segments, so they're right there together. If you're doing time-based kinds of queries, that's a very efficient way to do that. But we have more than one way of partitioning data at the data node level. So when a query comes in, obviously the query server is going to handle it, but then here is where all three of these things, the coordinated processing, the hybrid architecture, and the efficient storage engine, here's where they all come together, is at the moment of a query. So a query arrives, and the query server will basically distribute this to the data nodes that are relevant for that query. So we call that scatter, and then it gathers the results locally, usually, back to the query node. So scatter, gather. Now, we do use caching. We can cache at a number of levels. So we can cache in the RAM of one of these data nodes. Of course, we can cache from here. The query can be cached from the local storage, which is most common. And then if we need to, of course, we can bring data back all the way from the deep storage layer. So we have caching at each three of these layers when you do a query. So this is how you get sub-second response at any scale. You need all three of these things. You need a coordinated architecture, coordinated processing that is independently scalable. You need an architecture that can provide the performance of local response when you're running a query, but has separate storage and compute so that you get the flexibility to do things like scale out without having any downtime or even the need to do anything. It just handles it automatically. And then because we have, and this is key, we're not just columnarizing and compressing. That's not what we mean by efficient. We also mean that you have multiple choices for partitioning data, and the index is right there where the data is located as well. If you can do all of these things, you can deliver sub-second response at any scale. Well, I hope you enjoyed this short Druid Lightboard. I look forward to seeing you around the Druid community.